Assalamu alaikum dear students, welcome to my YouTube channels. In this lecture I will solve problem number 3.22 which is from chapter 3 and its number is 22. The statement of the problem is like this: consider a particle which moves in a scalar potential V of r is equal to Vx of x plus Vy of y plus Vz of z. Show that the Hamiltonian of this particle can be written as the sum of hx, hy plus hz, where hx is equal to px square plus 2m plus vx over f, and similarly hiv is equal to py square over 2m plus vy over y and plus pz square over 2m plus vz over z into z. Then in the second part, do hx, hy and hz form a complete set of commuting operator. Okay, in the first, in order to solve this problem, we recall the few things that Hamiltonian is equal to T total kinetic energy plus potential energy. So kinetic energy, you know that kinetic energy can be written as P square over 2m, and P square is equal to Px square plus Py square plus Pz square. Okay, so P square can be written Px square plus Py square, and we have this term in division, which is 2m dividing by 2 whole term, 2 px square over 2m plus py square over 2m plus pg square over 2m. So if we substitute the values of this t into this equation, so we will have h is equal to p square over 2m, which is equal to px square over 2m, py square over 2m, pg square over 2m, plus potential, which is the sum of three potential, because it is a scalar quantity. Is contain three term: potential of x along x, potential along y, and potential along z. So h is equal to this px square plus v of x is equal to nothing but vh of x, py square plus 2m plus vy of y is equal to hy plus pz square over 2m, and this term is equal to Hamiltonian for z axis, or for z. Okay, so there our we have achieved our aims, because our final task was writing Hamiltonian in term of hx, hy, hz in the summation form. So h is equal to hx plus hy plus hz. For the next part, do hx, hy and hz form a complete set of commuting operator. So for this, generally speaking, although all of the operators are commutative, though they do not form a common set of commuting operator because they are degenerates. Okay, we can prove this by many more methods, but first thing is that all of the comparator are commutative, means if we know that we take commutation of hx with hy, okay, they are commutative. Similarly hy with hz, this will give 0, and similarly hz with hx, so their commutator will be equal to 0, mean they are commuting with each other. And if they are commuting with each other, so they will not form a common set of commuting operator, because. And the second is, if we find the eigenvalues for hx, for hy and for hz, if their eigenvalues are degenerate, we have to cross check. The first is to check their eigenvalues. If their eigenvalues hx, eigenvalue of hy and hz are degenerates, it means they will not form a common set of commuting operator. And the second method is the commutative property. If the two operators are commutative, then it is not necessary that they will form a common set of commuting operator. But the second cross check is to check their eigenvalues. If their eigenvalues, two of eigenvalues are same, it means they will not form a common set of commuting operator. Like this, they do not form a common set of commuting operator because they are degenerates, means their eigenvalues are same. So definitely in this case we will have a check result that they do not form a common set of commuting operator. Okay, I think this was our final task.